I first want to thank the organizers for putting together the virtual conference and for giving me the opportunity to contribute. I've decided to speak about, well, a topic in random matrix theory, which I think, random matrices have not surfaced yet that much in this conference, but this project we solve via integrable systems and Poisson-Levé special function theory techniques. So I think, although the outset might not, align with the geometric flavor that we have seen so far, the results certainly do. And besides, I will include ample introduction to this project and to the background. Okay. The work overall that I'm about to share with you is here joined with Alex Little. Alex is a postdoc here with us in Bristol, and some of the results that I'm about to share with you, they will be part of, well, a forthcoming preprint on the archive later this summer or later this year. Okay. Now, what kind of overall topic do I have in mind? Well, ultimately, we will be interested in rightmost eigenvalues of some non-Hermitian random matrices. So up front, I want to give you a brief introduction to this, subject of analyzing rightmost particles in some models. Well, why is that a question of interest? Well, for that, you don't have to look far. You can go to, say, ecology, or here I write some phenomenological models. So what do I have in mind is, well, for instance, population growth models. So population growth models, think of them as modeled by some first order linear ODE system, the way it is written here. So we got unknown vector u, column vector on the left, derivative of that, and then on the right, you got some coefficient matrix x, and then times u again. So the coefficient matrix, say in the population growth model, it would encode the interaction between the different species in your model. So for instance, say you got a predator-prey model, the interaction matrix, the coefficient matrix x would encode how those species interact with one another. All right, so now to have a reasonable, good population growth model, of course, you need to know those interactions quite well. But now, of course, if you got several species in your model, this becomes more and more hopeless as the size n increases. And for that reason, it's not so far-fetched, and this has been done now for more than 50 years, it's not so far-fetched to include some degree of randomness in this matrix bold X. In fact, if you trace this back in history, I think Robert May in 1972, he was the first one to do this. He wrote a paper in Nature that turned out to be quite influential later on. Okay, so let's make this assumption. We're looking here at a stochastic linear ODE system, which is to say that this matrix X here, the coefficient matrix, is filled up with some random variables, and I'm not going to assume any symmetry constraints on X. So that's why I really think about a non-Hermitian random matrix X here. Okay, now, in this context, what is the question that you want to answer? Well, since it's a population growth model, you like to know what happens to your species in the model as the time evolves, right? Predator-prey. Some species might die out, another species, its population might level off. So you're interested, in other words, in long-time asymptotic behavior of your solutions to the system. In particular, you're interested in stability questions. Right. So now, if you think about stability questions for linear ODE systems, then there's a fully developed theory about this. What you're going to do is you're going to fish out equilibrium points of your system, and then you would expand your coefficient, your right-hand side, you would expand it near such an equilibrium point. And doing this local expansion business, this is really the reason why here my matrix X, from the get-go, I assume it is independent of the time, right? It's constant in time. Random entries, but constant in time. Okay, this is what Robert May did in 1972. He wrote this system in this form, which I have down here, equation number 1. So for simplicity, he put a minus identity, so deterministic term, to leading order, so that would create some exponential decay. And then the interactions, the random interactions, are sitting again in X, and then he put some scalar parameter G, coupling constant, in front of it. Now, coming back to stability, well, the eigenvalues of this coefficient matrix minus identity plus Gx, they're going to determine the stability of your solutions to the ODE, right? So in particular, the largest real part of the spectrum of this coefficient matrix, it will determine the overall stability. And that's why here you can now see why I'm interested in rightmost particle, right? Particles, eigenvalues, whose real part, is largest, right? Because they determine stability, right? And of course, this has been done for many, many years. There's a great interest in understanding accurately real parts of rightmost eigenvalues in large non-Hermitian random matrices. I will review some of that history in the upcoming slides. And our project that we did here with Alex is concerned with understanding precisely the statistical behavior of such rightmost eigenvalues in one particular, interpolating random matrix model. I will tell you what the guy interpolates between, okay? In fact, you should maybe think of this, sort of as a coin. You got two sides. I will now explain to you the two sides, and then the interpolating random matrix model, it will connect the two sides, and we investigated this connection on the level of the rightmost eigenvalue. Okay, so what are the two sides? Well, first one, both sides, I must say, that they're very, very classic stuff, of course. First one, Gaussian unitary ensemble. So Gaussian unitary ensemble, this is in a family of Hermitian random matrices. So how do you generate a matrix from the GUE? Well, you start with this matrix bold Y, which is a square matrix. You fill it up with IID copies of some complex Gaussian variables, as written here, and then you symmetrize. So you add a Hermitian conjugate to it. Right? This gives you a Hermitian random matrix. Now, this is one way how you can approach the GUE, maybe, some probabilistic flavor in the background, but you can also do it with statistical mechanics, of course. You might know, it's a well-known fact, that eigenvalues of a GUE matrix, you can think of them as a log-gas particle system. So those little xj's here, they would be the eigenvalues of the big bold X matrix up here, right? Those eigenvalues, they are necessarily real because you're dealing with a Hermitian ensemble, and well, they are distributed somewhat randomly on the real axis. The joint PDF for the particle's location is given by this extremely famous formula that is down here. Note, you start with a matrix Y that you fill up with independent random variables, but of course the eigenvalues of X, the one which is symmetrized, they are nothing but independent, right? There's a huge correlation happening here. There's a Vandermonde squared term, and then you got these products of the exponential factors. All right, this is all very old, very classical. Whichever way you choose, whether you come through this Porter approach or the StatMech approach, sooner or later you want to ask yourself this question and then hopefully answer it. How do the particles behave for large n? Okay. Now, of course, why is GUE so nice? Well, because you can answer this question explicitly through some explicit calculations, right? You can compute almost everything explicitly. So this started back in the 1970s, Freeman Dyson. Here, he was the first one who managed to compute these correlation functions. The correlation functions, well, this is this marginal here in the middle, and then you rescale it by n factorial over n minus k factorial. What Freeman did is he computed it as a determinant of a scalar, so-called correlation kernel, k sub n, right? This statement, this equation here, this sort of is what's hiding behind the statement that the eigenvalues of the particle in the log gas form a determinantal point process, DPP, on the real axis. Okay, now what's this kernel here? Well, in the GUE, this is just a Christoffel-Darboux kernel that you construct in terms of Hermite polynomials. So the capital H sub k, these are Hermite polynomials of degree k. Okay, you take two of them, x and y, and then you weight it with the normalizing constant, 1 divided by the normalizing constant, and then you sum up. Okay, this is a perfect Christoffel-Darboux sum. You could simplify it because the orthogonal polynomials satisfy three-term recurrence. Okay, anyways, and then to the far left, you got some, Gaussian humps. Okay, now this is explicit formula. And now what you do is, well, you go to Seger's book on Hermite polynomials. You can find all sorts of large degree asymptotics in it. And then having that knowledge at your hand, you will be able to analyze the correlation functions asymptotically in various scaling regimes. Right. I will focus on two such regimes. The first one is the global one. The other one will be the local one. Local meaning we study correlations between pairs of eigenvalues with respect to some suitable scaling. Okay. So first, the global though. So what you do there is, well, you count the eigenvalues, the particles to the left of some fixed point S. And then you divide by the total number. This defines what's called the empirical spectral distribution, ESD. This is a random measure, provided you, as usual, rescale everything, correctly. So you divide out square root n. Notice my ensembles, they are defined where the variances are independent of n. So I need to divide out, square roots of n. Under this scaling, almost surely that measure up there converges to an extremely famous target, Wigner semicircle distribution. Okay. Written here in equation number 2. The plus here means the non-negative part of the radical, right? I'm sure you have all seen, of course, these pictures a million times in your life. One more time now. So what you're looking at are eigenvalue histograms. These are the gray bars. You go to the computer, take a 2000 by 2000 GUE matrix, you rescale it with this, 1 over square root n. You compute the eigenvalue histogram. This gives you the gray bars, both on the left and on the right. On the right, this is for 4 by 4. On the left is 2000 by 2000. And then you compare the eigenvalue histogram, the overall sort of enveloping shape, to the exact Wigner semicircle curve in red. Of course, on the left for 2000 by 2000, you've got great matching. On the right, not so much, but you shouldn't, expect that, because it's just 4 by 4. But what you can do is you can just compare it to the exact eigenvalue density. This is the blue dashed curve. The exact eigenvalue density is readily available because this is the one-point correlation function. And for that, you have the formula in terms of the Hamid polynomial. So you just give it to your computer and then it spits out the blue curve. And the blue curve, of course, fits much better to the gray histogram than the red one. Okay, good. Now, this is the global stuff. And now looking at these pictures, the one on the left, say, you see now when you start studying now correlations between eigenvalues, local correlations, then you only need to worry about two scenarios, two qualitatively different scenarios, I should say. Namely, you can study correlations between eigenvalues in the bulk, and you can study correlations between eigenvalue near those, edges, so right or left. Then again, because I'm interested in rightmost particles, I will do the local analysis only on the far right, right? So near the right edge. Okay. Now, of course, I didn't do that. This has been done 30 years ago. If you zoom in on the right edge point, so for me, because of the normalizations, it's the square root 2n, and then you substitute this into your correlation kernel. You wiggle around it with the scaling and 1 over 6, x and y on compact subsets, then out comes the Airy kernel, right, as n tends to infinity. Very famous stuff. The Airy kernel here, I prefer to write in this way. So you take your two Airy functions, you have plus, and then you integrate out the intermediate variable. This gives you a nice kernel of an integral operator, which has all sorts of nice properties. In particular, this integral operator corresponding to this kernel, it then lets you write down the limit law finally for the rightmost particle, right? So, but here, since we're doing Hermitian model, rightmost means largest. Right? So, and this is this famous result up here. Also, almost 30 years old. So the largest eigenvalue in the GUE in distribution, you go to the right Wigner edge. That's to be expected, of course. And then the fluctuations, they are random. They are distributed with F2, which is the celebrated Tracy-Witham GUE limiting distribution. All right. So the CDF for that random variable, I will write here in two ways. The first one is Forrester 1993, which is the Fredholm determinant way. So earlier we had the Airy kernel. I said it defines a nice integral operator, and this is the K sub AI right in here. It is nice in that this operator determinant, is well defined and has all sorts of good properties. The other way, this is the one which is much closer, of course, to our conference right now, is the Poincaré way. So as you know, Tracy and Widom back in 94 famously rewrote this operator determinant in terms of a special solution to a Poincaré equation. As we progress here with the slides, I will gradually say more and more about that one. All right, good. So this is one side of the coin, which is GUE, and we know that the rightmost particle in the GUE, it obeys this, Tracy-Widom limiting statistics. Now, before I show you the other side of the coin, let me briefly emphasize that, everything that I've done so far was very specific, specifically tailored to Hermitian matrices with Gaussian entries, which is good because, you can give your students this as an exercise to compute the stuff. But the important point is these two limit laws, the Wigner semicircle, as well as here this Tracy-Widom edge law, they hold true in a much bigger class of complex Hermitian random matrices. This is much harder of an exercise for students. So if you are in the class of so-called Hermitian Wigner matrices, so those are symmetric Hermitian matrices that you fill up, accordingly, IID complex variables on the bottom, and then IID variables on the diagonal, provided you have some, good decay and finite moment constraints. In this much bigger class, you will still observe Wigner as well as the soft edge law up here. Okay, now let's sort of pivot. Let's go now to the other side of the coin, which is also classical, and you could call it GUE without symmetry. This is complex Ginibre ensemble. So complex Ginibre, well, you start as before. So you take this bold Y, which is n by n, and you fill it up with IID copies of these complex Gaussian, but then you don't symmetrize. Right? So this is now non-Hermitian matrix. It's classical. Ginibre in 65 defined it, and he was the first one to do again calculations. One of the calculations that he did is justifies the following statement, namely, you can also think here of a log gas particle system. So the ZJs, they are now your eigenvalues, so these will be in the complex plane because it's non-Hermitian, and Ginibre computed the joint PDF for the particles locations in his 65 paper. So the formula is here. As you see, this is very similar to what we had earlier. The difference being now the ZJs are just, complex variables. And up here, you got a rotational symmetry built in because we don't have ZJ squared, we got moduli squared. And this is extremely helpful in calculations. All right. Now, what do those calculations tell me? Well, eventually the answer, again, this question, how do the particles behave for large n? So going back to Ginibre, although I cite here Meta because Meta gave a cleaner proof of this. Again, what happens is the particles, they form determinantal point process, but this time on the complex plane, not on the line. Right? But the statement behind that is exactly the same as earlier, namely k-point correlation functions can be computed exactly as determinants of some scalar valued kernel k sub n. In fact, I would say that analyzing this guy, analyzing complex Ginibre, is even easier than analyzing Gaussian unitary ensemble, and this is because the correlation kernel is actually simpler. So earlier we had this Hermite polynomial business, right? We had Christoffel Dabou kernel in terms of Hermite polynomials, and I said now to do some asymptotics, you have to go to Seger's book. Well, here it's easier because it's just a truncated exponential sum. So Z, the star, W stars is complex conjugate. And well, as you see, as n tends to infinity, without any rescaling, this would have a limit. So in particular, studying the bulk limit in the complex Ginibre is super easy. Anyways, now let's do this. So first, again, global level. Well, empirical spectral distribution again. So you count eigenvalues. Now, earlier in GUE, these were eigenvalues to the left of a point S. Now here, since I'm in the complex plane, it makes more sense counting eigenvalues in the semi-infinite rectangle, right? So real parts to the left of S and imaginary parts below T, all right? So this depends on two variables now. Still, this is a random measure. You rescale again with 1 over square root n. The guy converges almost surely to uniform distribution on the disk. This is the circular law. So Ginibre was the first one in 65 who computed this law for the ensemble that he had just defined in the same paper. Right. So here's the pictures, which are quite nice. Right. So what you're looking at there are complex planes, 3 of them. You take on the left a 4x4 complex Ginibre matrix. So you compute the 4 eigenvalues, and then you repeat it 1,000 times, which gives you 4,000 blue dots. So if you were to count this, you would end up with 4,000 blue dots. And then you increase the size, to 8x8, 16x16, and you get more and more blue dots. And you compare this to the red curve, which is, as you can see from the picture, this is the unit circle. All right. Good. Right. Earlier in GOE, I also gave you pictures of eigenvalue densities, and you can do the same here. Remember, I said earlier eigenvalue densities, they are essentially one-point correlation functions. So, but you have a formula, right? The one-point correlation function, this is just like this kernel on the diagonal. So Z is equal to W. So when you do this, you see that the result, it just depends on 2 real variables, right? When Z is equal to W, it depends on the real part and the imaginary part of Z. Right? So if I now show you plots of eigenvalue densities, necessarily these have to be 3D plots, right? And I generated 3 of them here, right? So X and Y, this would be real part of Z, and Y would be imaginary part of Z. And then the vertical Z axis, this gives you the density as a function of 2 variables, X and Y. And as you see, as the size increases, so 550, 250, you see very nicely on top this plateau shaping up, which will be the unit disk, right? Because the eigenvalue droplet is the unit disk. Okay, good, nice. Now, next thing, local correlations. So again, eventually I'm interested in rightmost particles, rightmost eigenvalues. So I will only do this here on the edge. The bulk, I gave a reason earlier why this is actually easier. So let's only look at the edge. For me, edge means because my variances are n independent, so I need to look at a point which is distance square root n away from the center, right? Not distance 1, because I need to rescale everything. All right, so anyways, you do this, and then you wiggle around with square root n scaling. Out comes what's called the complex Ginibre edge kernel, so E, and this guy is defined in terms of complementary error functions. There is one parameter still remaining because you're in the complex plane, right? So going distance square root n out, you can still do at an angle, and that's theta, right? The argument of Z0, and which appears here in that limit. Okay, good. Now having this one, now you can write down limit theorem for rightmost particle. And here, because you're doing a non-Hermitian model, really rightmost means largest real part. Okay, so here's the limit law. So the largest real part of eigenvalues in the complex Ginibre ensemble as n tends to infinity. Well, again, you creep up to square root n. Right? That's to be expected from the circular law. But then the fluctuations, they are somewhat more sophisticated. So the centering here and the scaling is more complicated than earlier in the GOE. But the benefit of non-Hermitian here is that the limiting distribution is actually much simpler. So this G, this is a Gumbel random variable. So it has a very simple limiting distribution function. That there is no Poincaré special function theory in this business. Okay, the limiting distribution is much simpler. All right. You might know, so this is very young actually, this result, 2022, it was this summer. You might know another result about complex Ginibre, and this has to do with the limiting distribution of the spectral radius. So spectral radius just means the complex moduli, and then you look at the largest. And surprisingly, or maybe not, the spectral radius satisfies formally the exact same limit theorem than the one which is written up here. So Gumbel for gamma n and gamma n over 4. The only difference is when you do this for the spectral radius, the gamma n is defined slightly differently. Okay, but formally the exact same structure that comes up. Okay, good. Now, final comment about complex Ginibre is again about universality. The benefit of having Gaussian entries, as I said many times, is because you can do exact calculations, but these two results, the circular law as well as this edge law, hold true in a much bigger class of complex non-Hermitian matrices with IID entries. Okay, I will leave it at that. All right, so now we have our two sides of the coin. The first one was GUE, rightmost particles obey Tracy-Witham limiting statistics, and now here in the complex Ginibre, which is non-Hermitian, rightmost particles obey Gumbel limiting statistics. Now the model that I'm going to introduce now, it will allow me to interpolate between these two extreme value statistics, and we will try to figure out what kind of integrable system achieves this interpolation, right? Because in Tracy-Witham, we got Poincaré 2, and here in Gumbel, we got something extremely elementary, e to the minus t. So what kind of integrable system interpolates between these two functions? This will be the ultimate goal of this lecture. Right? So, but first the model. Now, frankly, there's many ways how you can interpolate between a Hermitian and a non-Hermitian random matrix model, but probably one of the more famous one, maybe even the most famous one, is this elliptic stuff. So complex elliptic Ginibre ensemble, E-Gin-UE. So first I have to tell you how you get a matrix in there. Well, you start with two independent GUE matrices, so X1 and X2. I told you earlier how you tell your computer how to simulate those. And then once you have these two, you look at this combination. So here is 1 plus tau over 2 square root X1, and then imaginary unit and another one. So this guy, it involves another parameter, but that's to be expected because I claim it to be an interpolating model. So tau is a real number between 0 and 1. Now let's do quickly some consistency check here. So when tau is equal to 1, then the second term here is 0. And the first term, that's why with the 2, this gives you exactly 1. So in other words, tau equal to 1 corresponds to a GUE matrix, whereas when tau is equal to 0, then these guys here, the square roots, they contribute equally. And then if you think about it, you're actually simulating a complex Ginibre matrix. All right? So in other words, tau allows me to interpolate between GUE and complex Ginibre. All right, good. You can think about it like this. You can also do the StatMech as usual. The eigenvalues here of X in the complex plane, because this is a non-Hermitian model, they form a log-gas particle system, and the joint PDF of the same system is given by this formula written down here. This is not due to Ginibre, it's just the technique that you use in the computation is due to Ginibre. That's why I give the reference. All right, you see the tau appears up here in the exponents. Okay. Last time, how will the particles behave for large n? Now, it turns out this is also an exactly solvable model, which is great. So in particular, eigenvalues form a determinantal point process. So this was proven by one of the speakers who spoke earlier this week, Di Francesco. There was also Itzigson and Godin in this 1994 paper. So what they managed to do is they managed to compute the k-point correlation functions, again, as determinant of a scalar kernel kn tau, and kn tau, well, okay, that's a bit more complicated, but it's written here. So again, we're back to back to Hermite polynomials, and then you got this tau to the power k also here, in the front, and okay, you got these exponential factors to the left, right? Now this is a bit more complicated. This is not a Christoffel-Darboux sum. But still, when n tends to infinity and tau is away from 1, then you can actually sum up this series. This is Mailer formula, and this helps. This helps. Okay, good. So now let's use the formula and do some scaling analysis. So again, two regimes. The first one, it will explain why this is called elliptic model. Probably no. So if you look at the empirical spectral distribution, now it will converge almost surely to uniform distribution on the ellipse. That's why elliptic model, right? And you see how the major axes depend on this tau. Oh, sorry. When tau is equal to 1, the ellipse is perfectly symmetric. When tau is equal to 0, the ellipse is perfectly symmetric, then it's the circle. And when tau is equal to 1, you see that the vertical axis, it collapses to the real line, you know, and that's what you would expect. Here's some pictures. So eigenvalue droplets for varying values of tau of a 10 by 10 complex elliptic rescale Ginibre matrix sampled 500 times, and tau equal to 0 on the left, and 1/4, and then 3/4 on the right. Okay. Now let's look at local correlations. Eigenvalue densities you can also plot, but I didn't do it, you know, this time. Now local eigenvalue regime. So this is now more interesting. And why? Because you got two parameters in the model. You got the matrix size and you got tau, right? So it's clear there will be a rich, you know, asymptotic landscape, so to speak. You could first do this, and this was historically the first thing that happened. So people looked at large n limit, but they kept tau away from 1. So tau equal 1 corresponds to Hermitian model, right? So they kept it away from 1. And then, of course, what you do here is you study actually local scaling limits of a genuinely non-Hermitian model. That's why this limit is called the limit of strong non-Hermiticity. Was worked out, Peter Forrester, Jankovici, 1996, but that's not the limit I'm going to be interested in. In my title, it says at weak non-Hermiticity. And why am I not interested in this? Well, whatever comes out here, which is interesting, you know, in its own right, but it won't allow me to interpolate between GOE and, you know, a Ginibre ensemble, right? It won't. What will allow me to interpolate between these two guys is the so-called weak non-Hermiticity limit. So now I will finally explain what these words in my title mean. Well, they mean you study scaling limit when both matrix size goes to infinity and the, you know, non-Hermiticity is killed off. So tau goes to 1, right? In some suitable way. Now, this is a limit that was first studied by Jan Fyodorov in 1997. I will briefly tell you how it works. Well, unsurprisingly, everything depends on a certain combination of n and, well, say 1 minus tau. So here's the combination. You take a sequence tau n, which converges to 1. So the second factor here, 1 minus tau n, I mean, the square root is technical, so, but okay, let's accept it. This will go to 0, and then the alpha, that exponent, will be positive. So this factor goes off to infinity, and then it's clear everything will now depend on the behavior of sigma n. Only two things can happen. Either sigma n escapes to infinity, this will give me 1 limit, or it attains a finite non-negative limit. This will give me another one. And in turn, with this, I will be able to interpolate between GOE and GNUE statistics. So Hermitian and non-Hermitian statistics. And we are going to do this on the level of the rightmost particle. So we're going to interpolate between extreme value statistics. Okay. Well, when I say we, I have to say, of course, this has been done before. So Martin Bender in 2009, he did this for the rightmost particle. Right? So what is Bender's result? So these are my eigenvalues, Zj. Bender viewed them as points in the two-dimensional real plane. That's fine, right? So xj would be the real part and yj would be the imaginary part of Zj. Fine. Now, what did he do? So he worked out in his paper the centering and scaling constants. They are written in the paper. I won't show them to you. Critical exponent at the rightmost particle at the edge is 1/6. And then he proved that the resulting eigenvalue point process, which is determinantal in the two-dimensional real plane, only two things can happen. And two, that should be clear, because I said only two things can happen to the sigma n, either to infinity or to a finite limit. Right? And so, accordingly, when it escapes you to infinity, that process converges weakly to a Poisson process on the plane. And if it doesn't, if it attains a finite limit, call it sigma, then it will converge to something else. And something else he called the interpolating Airy process, again on the plane. Now, these two processes are both determinantal point processes. They are defined through these kernels. This is the correlation kernel for the limiting Poisson process. So Zk, these are two-dimensional vectors, so they have coordinates x and y. All right, here's the kernel. And the interpolating Airy process, I will show you on the next slide. It's a bit more complicated. What I want to say before that is, These are determinantal point processes. These limiting guys are determinantal point processes, and they have rightmost particles almost surely. And now what you expect to happen? Well, if you compute the distribution function of the rightmost particle in this one, in the Poisson one, you will get Gumbel distribution, as you should, right? Because sigma n going to infinity really means the non-Hermitian part survives in the limit. And then you know from what I told you earlier, you should expect Gumbel behavior, and that's what comes out. Now, interpolating area process is more complicated, so it's defined by this kernel, right? Looks, at first glance ugly, but there is structure. So you got, again, two area functions. The S is the one that you integrate out, and then there's sigmas placed at various, positions. And, again, zk is xk, yk, so the x's are everywhere, right? That's the interpolating area process. Defined by this correlation kernel. And then what Bender did, I already said, this guy has a rightmost particle almost surely. He computed its distribution function, limiting distribution function. Right, so this is hidden in the random variable B sigma, and Bender's result was he showed that the distribution function for B sigma, in other words, the limiting distribution function for the rightmost particle, it's given by a Fredholm determinant. So the Fredholm determinant of precisely this kernel up here on the same slide. Okay, so but this here you have to read carefully. This is integral operator acting on square integrable functions, but then on this higher dimensional domain. So T infinity cross R, right? Okay, fine. So now here's the project that we now solve with Alex. We know the interpolating model, it interpolates between Tracy-Witham and Gumbel behavior. So now the question is, all of this is buried in this Fredholm determinant. Can you write out any sort of integrable system for this Fredholm determinant? Okay, that was the project. In fact, this was a question that people in the field, such as Gerhard Ackermann, had asked us for a few years. And the answer here is, well, it's already spoiled in the title. Poincaré special function theory captures that interpolation. Okay. Good. So here, let's first read the result, then I will talk more. So here's the formula. So the limiting distribution function, this is this ft sigma. So Bender wrote this as a Fredholm determinant. So this is a distribution function in T, which depends parametrically on sigma. Now here's the formula. It is e to the minus t infinity s minus t, as in ordinary Tracy-Witham formula. But then it differs from Tracy-Witham, because in Tracy-Witham, now what you would have is you would have a Poincaré function squared, depending only on s, and then you integrate out the s. But here it's slightly different. You've got an antiderivative of the square of a special function, which depends on two variables, s and lambda. And lambda, that's the one that you integrate out here in this inner integral. There's some measure mu sigma involved. Okay, fine. Which has a density which is written here on the right. Okay. So, but now, of course, what is Q? What is the special function? Well, this satisfies an integral differential version of Poincaré 2. All right. So the main variable here it would be s. Down here I write it as t. Would be t. So you got second derivative. Respect to t, fine, is equal to t plus y, so that's slightly different, t plus y times q, and then in ordinary Poincaré 2, you would have twice times a cubic term. So here, the cubic is generated by taking antiderivative of a square and then multiplying it by power 1. All right? So that it is really an integral differential version of Poincaré 2. Of course, you got to be careful. This is just an ODE, so you got to select, a distinguished solution, and that is achieved by enforcing the boundary condition. All right, so now, before I move on, let's do some consistency checks here. So when sigma goes to 0, then we expect this formula to reproduce the Tracy-Witham formula. And can you see this? Well, look here. So this density here, of course, when sigma goes to 0, this becomes delta function with mass at 0. So in other words, this integral here in the curly bracket, it goes out. It just gives you a square term at lambda equals to 0. Okay. Now, if you look at the differential equation of the dynamical system down here, similar thing happens. When sigma goes to 0, that integral will drop out and you will get square term here. And then it would be just the ordinary Poincaré-2 equation, but the variable is not t, it is t plus y. Okay, that's how it differs from the ordinary Poincaré-2 Hastings-McCloud, in that the variable sort of comes with this shift. But you see, then again, the shift you should expect because it's already written here in the boundary condition, t plus y. Okay, so, oh no, this is a bit hand wavy, but really when sigma goes to 0, this reproduces ordinary Hastings-McCloud Poincaré-2. Now, sigma going to infinity, this is more challenging. You need to center and rescale this t with some appropriate powers of sigma, but then it will spit out the Gumbel formula. Right? So this guide, it really interpolates between this Gumbel distribution function and the Tracy-Widom distribution function, which is given in terms of Hastings-McCloud Poincaré-2. And the interpolation is achieved by integral differential Poincaré equation. Okay, good. Now, let me discuss a few consequences of this guy. So first off, then I will also tell you a little bit about how you can prove this. Now, the first consequence is, so Bender's formula is quite complicated in that, you know, you got this Fredholm determinant, the kernel is, you know, kind of messy, say, and then also you have these higher dimensional integration domains appearing there. Now, first consequence is that once you have this orange box here about integral differential connection, you actually have a cute corollary, which shows that actually this more complicated Fredholm determinant is somewhat simpler. Namely, it's just a Fredholm determinant of an integral operator L sigma and then acting on a one-dimensional integration domain. So here on the middle, it is t infinity cross r, whereas on the right, it's just the interval t to infinity. And what is L sigma? Well, L sigma is one of the guys that Mattia Cafasso, right after me, will focus on. This is what's now called a finite temperature Airy kernel. Right? So what is a finite temperature Airy kernel? Well, the ordinary Airy kernel, you just take these two Airy functions, you integrate out the z, and then say from 0 to infinity. That's the ordinary Airy kernel. Now, what has, you know, been called finite temperature Airy kernel, there would be some weight next to the Airy functions, and then you integrate over the full axis. And now this weight, of course, it has to, you know, achieve convergence because the Airy functions at minus infinity aren't that great, right? So, but this is then achieved with suitable weights. And for us, the weight is the CDF of the standard normal random variable. So phi, like you write it in your class in probability. So that this is our weight. Now, such kernels and associated Fredholm determinants, they have popped up, I would say, over the past 10-ish years, maybe. It started with integrable probability. I'm probably, Mattia will say more about this. And then recently also in theoretical physics, some quantum gas models, they were shown to be related to this finite temperature stuff. But there the difference was the weights, they were maybe a bit simpler, I would say. So the appearance of this Gaussian CDF here, this is really a feature of our model. But nevertheless, so this appearance here, our result with Alex, is really the first appearance of integral differential Poincaré functions and finite temperature Airy kernels in random matrix theory. Of course, now you can say there was Johansson in 2007. He has this MNS model, Moshe Neuberger Shapiro model, where he also had a finite temperature Airy kernel, but back then he did not connect this to integral differential Poincaré functions, right? So by me saying this is the first time that integral differential Poincaré functions appear in random matrix theory, this is really a fact. Okay, good. Now, how do you prove this fact? So when we have few trouble along the way. First one being that our integral operator looks, you know, kind of challenging, and then there's this two-dimensional, you know, business. So, but it starts with some, you know, miraculous trace identities. So using, you know, simple things such as Cauchy theorem and various integral identities, you can actually show that the operator traces of this ugly guy, Ki sigma, They turn out to be operator traces of something which looks easier, at least on the eye. And the easier one is written here in equation number 7. Right? These trace identities in particular mean that the Fredholm determinants of the two guys are the same. Right? So, and why is this one easier? Okay, it looks easier. So it's just two Gaussians, one on the left, one on the right. And then in the middle, you have the ordinary area kernel that I had at the very beginning of this talk. Just the ordinary area kernel. And you see how here sigma couples the variables, right? So indeed, when sigma is equal to 0, then horizontal and vertical variable decouple. And that's why your Fredholm determinant just reproduces the ordinary area kernel determinant. Okay. Good. Now, all right, so what, right? Is this a useful identity? Well, the answer is yes. That's why I like it, because this identity identifies this operator K sigma as an additive Hankel composition operator. What do I mean by that? Well, I can now rewrite K sigma in this simple form. So there's there's one function in two variables, phi sigma, phi is written here. And you see the sum of arguments is appearing in the first variable. So this means, if you interpret this right, this means this is a Hankel composition operator in the first variable, right, in the x variable. And now this I can use as a stepping stone in deriving the integral differential connection. There has been work by myself and also by Alex Krajenbrink in theoretical physics over the past 2 years, where we developed some methods how when you face such a kernel, how you can then, in a rather systematic fashion, pull out the integrable system. Right? And applying this kind of framework here, it will lead you cannot do it as an exercise if you know this, to integral differential Pauli equations. And here, because, well, we have these area functions, it will be integral differential Pauli too. Okay, appears quite natural. Good. Now, some other consequences of this. Well, I mean, once you have the integral differential connection, now it opens you, I mean, it's a formula, but so what? But because it opens you, doors and ways to study, say, tail asymptotics. So, because this is a distribution function in random matrix theory, so you might be interested in tails. Again, this is distribution function only in the first variable. It's not a distribution function or a joint distribution function for that matter. All right, so, but now for tail asymptotics, now, this is because of the presence of sigma, it is more challenging than say doing tail asymptotics in GUE or in complex Ginibre. But nevertheless, so I don't want to bother you with many technical details here. What I want to say is, once you have the integral differential connection, there's a systematic, although still technical way that allows you to pull out tail expansions for this, distribution function. So here's at plus infinity. There's two scaling functions, A and B involved, which are explicit. The formulas are here. But this doesn't capture everything uniformly in sigma, right? So what I want to do is I want to study t goes to plus infinity uniformly for all positive sigma. This only works, equation 8 only works when sigma does not grow faster than, some power of t. So beyond this point, you have to do a different analysis, and then equation 8 is replaced by equation 9. Notice everything is explicit here. All leading order terms are fully explicit in terms of some scaling functions. So here it's C and D, which are antiderivatives of ln's of, this Gaussian CDF. Right? And sure enough, when this ratio, t over sigma, when it goes off to plus infinity, so t dominates over sigma, then formula 9 reproduces formula 8. So in other words, these two, they overlap, right? And in turn, put together, they capture the full crossover between the right tails in Tracy-Witham, which is written here on the left, and Gumbel, which is written on the right. And this is surely a, somewhat of a non-trivial transition, because Tracy-Witham right tail goes down, or approaches 1, I should say, as this minus 4/3 t 3/2, whereas the Gumbel one approaches 1 just with minus t. So if you want to know how this can change from t 3/2 to t, well, these two formulas, they tell you. Okay, good. There's a similar story for the left tail, which is more complicated. We have some things under control, other things we don't have under control. So I will just say this is work in progress. Okay, so now I will essentially start wrapping up things. I have been talking about extreme value statistics, rightmost particles. But of course, you know, you can also ask now what happens in the bulk. And I just want to give you a short bulk excursion about this. So in the bulk, let's go to G. So what do I mean by bulk statistics? Now, yeah, how do gaps between consecutive bulk eigenvalues, you know, behave in the GUE? And then you know, similar thing in the Ginibre world. So you take you take consecutive real parts of eigenvalues, say in the bulk. What can you say about the statistics of those gaps? Now, yeah, doesn't require much imagination, but what comes out are some, you know, bulk generalizations of this interpolating Airy kernel that I had earlier. So this is what people call the interpolating sign kernel. It defines the determinantal point process, but let's forget about this. Let's just look at the kernel. So this is written here. This is a generalization of the sign kernel, if you wish. And then in turn, in turn, the Fredholm determinant of the sign kernel in the GUE, it is replaced by a Fredholm determinant of this sort of interpolating sign kernel. Again, kernel looks more ugly, but fine. And the problem really for the analysis is that you are again on some two-dimensional domain. Okay. So, but you probably know, so sign kernel determinant, this relates to some Poincaré 5 equation. So now what happens when the sigma is non-zero? Can you cook up some, you know, generalization of this, you know, Poincaré 5 system? And I mean, it's not a surprise now. Earlier, what I did is I used integral differential Poincaré 2, and then sure enough, here will be some integral differential Poincaré 5. So it generalizes quite nicely. Okay. I will give you a little hint how you can prove all of this. So again, it starts with some trace identities. So my suspicion is that there's some universal underlying feature that we don't understand yet, but that feature guarantees the existence of such beautiful identities. So what happens here is this interpolating sign kernel that I just showed you. Again, you can transform the operator traces to a simpler guy. And you see here, there's a typo. So here's S sigma. This should also be S sigma in equation 10 on the left. So you notice here, this is the exact same structure that we had earlier at the edge. The only difference is now that you're on the bulk, the guy in the middle is not the edge kernel, but the bulk kernel of the GUE. It's just the ordinary sign kernel. Everything else is exactly the same. However, there is a difference because the sign kernel is not a Hankel composition kernel. This is a Wiener Hopf kernel, right? So it depends on the difference of the arguments rather than the sum. Okay, and that changes now something, but okay, we know how to circumvent this. We know how to prove determinantal identities. And then what comes out is a simpler Fredholm determinant with a so-called finite temperature sign kernel. Why again finite temperature? Well, because it involves a weight. I've written out the weight here explicitly, but you know, you can close your eyes. It's not important. Oops. What's important is this 11 really generalized sign kernel, because if this weight here is just characteristic function on -1 to 1, then this is exactly the sign kernel written in this integral form. Now here it's not, because you know there's some other weight, but nevertheless now there is a machinery. I already did this a year ago, never published it, that allows you to pull out integral differential Poincaré 5 equation for the corresponding Fredholm determinant. I never published this because I didn't really have a good motivation for doing it, but now that we figured out this actually appears in Ginibre model, in elliptic Ginibre model, now we will do it. Okay, I think I'm done. So I will close out with these two pictures because they kind of, you know, sum up what I've been doing. So we have Harold Widom and Craig Tracy on the right, because Tracy-Widom distribution function, it appeared up front. And then here in the older picture, this is Emil Gumbel, because Gumbel distribution appeared. So if you're interested in some models that allows you to interpolate between these two extreme value distributions, Gumbel and Tracy-Widom, then the complex elliptic Ginibre ensemble will provide you a source, and the interpolation between these two extreme value families, it is achieved by integral differential Poisson-Levis functions. Okay, I will leave it at that. Thank you very much for your attention.
Okay, thank you for your talk. Are there any questions?
There's something in the chat, but I don't see my chat right now. Just a second.
It was something sent by accident, I think.
Yeah, it was a mistake. I was supposed to speak with Mark. Sorry.
Oh, okay. Okay.
Okay, so if there are no questions, then thanks again, and